In this video, we're going to talk about a few important features of quadratic functions and sort of in ascending order of importance. So the first thing we'll look at is a form of the distributive property, which often a lot of people call foiling. I don't really prefer that label because foil is a very specific use and can't be generalized all that easily. So let's just think about an area problem. Let's just think about situations in which we've dealt with area. So we know that area is a measure of basically the amount of space something takes up. So let's say that we have a 2 by 5 box. Okay, well we know that the area of this would be 2 times 5 equals 10 units squared. So if that were feet, it would be 10 square feet. If it were inches, it would be 10 square inches, etc. Now let's suppose that we were to extend this box by, I'm going to be very generic here, and I'm going to say, let's say we extended it by x feet in both directions, or x units. So we're going to extend it in both directions by x units. Hence we're going to be forming a larger sort of rectangle. So this would be x, and this would be x. Okay, so what would the area of this new box be? Well, we know that this side in combination would be 2 plus x, and we know that this side would have a measurement of 5 plus x units, because that's how we measure length, right? We add things together to figure out the total dimension. So in other words, instead of 2 plus x, I could say x plus 2, because we know that adding doesn't matter, the order of addition doesn't matter, and similarly here I could say x plus 5. Okay, so here is where a lot of people would go through foiling. But rather than to do foiling, we'll try to develop this method in a more intuitive way. Okay, so instead of doing that, because obviously at first glance you don't really know how to multiply this through, unless you have some sort of rule established already. But what I've done here is I've divided this box into 4 different regions. So what I can do is figure out the areas of these individual regions. So for instance, this box has a length of 2, a width of 5, so this has an area of 10. This box here is 2 units long by x units wide, and 2 times x is simply written as 2x. Again, same idea here. The length is x, the width is 5, x times 5, well, it's the same thing as 5x, or 5 times x. And this box over here, you probably guessed it by now, is x by x, which is x times x. A simpler way of writing that is x squared. Okay, so what have we come up with? Well, we want to know the area of this entire thing. So if we know the area of the individual 4 pieces, all we need to do is add them up. So I'm going to start with my biggest term, the term with the biggest exponent, which is x squared. Now I'm going to look at anything with an x in it. Well, I have 2 x's here, and I have 5 x's here, so that's a total of an additional 7 x's, plus I've got the remaining area here, which is 10 units, 10 square units. Okay, so essentially what I've done is I've multiplied every single component of the length by every single component of the width. So I've done 2 times 5, 2 times x times 5, x times x, and a lot of people think about this as foiling. So they think the first times the first, in other words, x times x, which gives me x squared. Then they say, well, everything in this parentheses multiplies by everything in this parentheses, so it's kind of like a distributive property. X times 5 is 5x. Well, hey, that just happens to be this little segment here. 2 times x, that stands for inner. We do the inner terms, and 2 times x is 2x, which gives me this guy here. And finally, the last term in this parenthesis and the last term in this parenthesis is 2 times 5, which gives me 10. And so then I combine all those pieces and I get x squared plus 7x plus 10. This area approach gives it more of an intuition, whereas this approach kind of makes you really forget what you're doing. And this method works regardless of how many terms you have. So, let's make this more generic now. Let's say that we have 2 factors, so factor is something that multiplies by another thing, so I have two factors here. And let's say that one of those contains what we call a binomial, something that has two terms. We'll call this a binomial. And multiplying it by something that has 1, 2, 3 terms, so we call that a trinomial. And the basic idea is very much the same here. We have a factor times a factor, and we can think about this in the area problem. So what I would do is create a box here that represents all components of each of the expressions. So x minus 2 I can think about as something that starts with length x and then is, well, I'm going to say increased by a length of negative 2. So in reality it's decreased, but I'm going to create its own separate little extension here. Similarly, I can do the same thing here. I can say it starts off as x squared, then increases by 3x, and then increases by an additional 7 units. So really what that creates is 6 separate boxes. And to find the area of all 6 of these, I just have to multiply the row by the column. So x times x squared, well, is x to the third. X times 3x is 3x squared. X times 7 is 7x. Negative 2 times x squared is negative 2x squared. Negative 2 times 3x is negative 6x. Negative 2 times 7 is negative 14. And now, because I want the total area, I just add up all these components. So I have an x to the third, that's my biggest power, so I'll list that first. Just kind of common way to do that. Then I have x squared, so negative 2x squared and 3x squared. Well, if I add those together, I have negative 2 copies of x squared, 3 copies of x squared. That means I'm up just 1x squared. And then I have my x's, negative 6x, and then I have a positive 7x, which means I have a net difference of 1x. And then I have my constant of negative 14 here. So that's how that would look if we were to quote-unquote FOIL it out. But the FOIL thing doesn't work here because we have 3 terms here and we have only 2 terms here. So that's an idea that sometimes I prefer the area approach, because as long as really we remember to multiply every term in this parenthesis by every term in this parenthesis, we're basically doing the same thing. So x times x squared, x times 3x, x times 7, you see that happening 1, 2, 3. Negative 2 times x squared, that goes here. Negative 2 times 3x, that goes here. And negative 2 times 7, that goes here. So for every term, I like to just set up a little area box in which I can very easily find out, what value goes in each box, and it saves me from making any possible mistakes when doing so. So suppose we have this equation, h of t equals negative 16t squared plus 100t plus 10, which is a model that describes the height of an object in feet as a function of time in seconds, since the object was shot at an initial speed of 100 feet per second from a height of 10 feet. Acceleration due to gravity is negative 32 feet per second each second, which is twice the value of a. What we're going to do is we're going to find the vertex of this equation and describe its real-world meaning. So first of all, going back to these ideas of interpreting the values of a, b, and c. So we know that our input is t, our output is the height as a function of t, and first of all we'll think about what these represent. So this is the number of seconds that has passed, this is the number of feet, or the height of that object in feet, and if we were to sketch this, we know that the object starts initially at time 0 at a height of 10 feet. Now we know that it's thrown at 100 feet per second. This is our initial rate of change, which, remember, rate of change is output over input, so this would be our feet per second. So if it's thrown upward, well, it's positive, so it means it's an increase of 100 feet per 1 second. So there's 1 second, let's say, an increase of 100 feet. And that increase is decreasing by 2 times negative 16. So as every second passes by, my change in height actually becomes a little bit less, so my slope decreases. And I'm not being very specific here in terms of making that decrease very obvious, but eventually what's going to happen is, as this arrow sort of starts to decline in the amount of elevation, it'll start to drop back down, and as we know, eventually at some point in time, this object will hit the ground. Well, that point at which you change from a positive rate of change to a negative rate of change is called a vertex. So this point here is called the vertex, and the vertex, another way to describe that is the maximum or minimum point of the quadratic function. By the way, the graph of the quadratic function is often referred to as a parabola, and so this shape here that you're seeing is called a parabola. And its maximum point, so this is called the parabola, this shape that has a frown or a smile, one of two ways that we can often see it, depending on the values of A, B, and C, or it can also look like this. Okay, so in this situation, well, the maximum point, if you think about this as a roller coaster, let's say you're staring at this roller coaster from the side, and you see that people are climbing up and eventually get to the top and then fall back down. Well, at some point they've reached their maximum height. Similarly, if that roller coaster is going from left to right in this parabola, down right here, it's going to reach its minimum point, and that point is called the vertex. So this shape is called a parabola. Both of these are called parabolas, and the point at which you reach the maximum or the minimum, depending on how it opens up, is called a vertex. Okay, well, how do we find the vertex? Well, we'll go back up here for a second. We know that in the problem where the height of the object reaches its maximum point here, what's driving that? What's causing it to reach its maximum point? Well, we know that, number one, gravity is causing an object to slow down. So if you threw something up in the air, you would notice that at first it travels a lot, the next second it travels just a little bit, eventually it comes to a stop and it travels down a little bit faster, 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 faster. We've all heard of the people shooting guns on New Year's Eve and 4th of July, and bullets basically falling from the sky and killing people because that object accelerates because of acceleration. Acceleration due to gravity. So gravity causes an object to speed up as it approaches the ground. In free fall, of course. So we know that eventually this thing's going to hit the ground, but also we know because of the coefficient of the squared, or the quadratic term here, the negative 16t squared, we know that the slope is leveling out. That initially the slope is 100, but then the slope is only 84. And then the slope is only 84 minus 16, which is 68. And eventually that slope reaches 0, and that's where the vertex occurs. So I'll let you kind of make the judgment on how this connection can be made, but the vertex location is at x equals negative b over 2a, only if the equation is of the form y equals ax squared plus bx plus c. So in other words, only if this thing is quadratic will it have a vertex. Linear equations, we know, continue to increase or decrease forever and ever. And then we know that c is the initial value. The b, remember, if you were to cross out the ax squared, it would look like a linear equation. So it's the initial rate of change. But then if you take 2 times a, you get the change in the rate of change. And to locate where that maximum or minimum occurs, we would take the negative of b